We are now going to look at ways to calculate the enthalpy change, entropy change, and Gibbs free energy change for reactions as standard states utilizing tabulated data or data that is in tables. To do this, we're going to first define what our standard state is. Standard state for a substance is defined by the following rules. Number one is that a pure element in its physical form that is the most thermodynamically stable at 1 atmosphere and 25 degrees Celsius or 298 Kelvin. So let me just back up here a little bit. So notice that it says if you have a pure element, it has to be in the form that is most thermodynamically stable, right? Element in most thermodynamically stable. What that means is that if we have an element like hydrogen, for example, you would not, so hydrogen by itself would not be the most thermodynamically stable. On the other hand, hydrogen as H2 would be the normal way in which we find this atom. So H2 would be it. Same thing for oxygen, for example. So oxygen by itself, that would not be the most thermodynamically stable form. On the other hand, O2 would be it, and so on and so forth. So you have to remember your diatomic gases. Those would need to be in that particular form. Or for things like carbon, carbon in the graphite form would be the thermodynamically stable form, while the carbon diamond would not be it. Now the second part is that if you have an element, it has to be at 1 atmosphere and at 298 degrees Kelvin. If you have a gaseous compound, it needs to be at a partial pressure of 1 atmosphere. Again, this is the partial pressure for the gas. Then if you have a solid or liquid, they need to be compound, it needs to be pure. And finally, if you have a solution, then the solute concentration has to be at 1 molar. So if you're given an example where you have one or two substances that are dissolved in an aqueous solution, you would need to see that the concentrations of each of them is equal to 1 molar. Similarly, if you have a mixture of gases, let's say reactants and products, each of them would have to be at a partial pressure of 1 atmosphere for it to be at standard state. All right, so how do we first calculate the enthalpy at standard state? This actually is an equation that you learned in General Chemistry 1. It said that you could go to a table to find the enthalpies of formation of each of your reactants and products, and then you could utilize it to put it into this equation to find the enthalpy of the reaction. So first, before we go into the equation, notice that we're utilizing this little zero to indicate standard conditions. You will see this little zero being used with the enthalpy, the entropy, and the Gibbs free energy. And it means that we are, again, at 298 Kelvin, that we have pure elements or compounds in their thermodynamically stable form, that if we have a pressure for a gas, it would be 1 atmosphere. If we had a solution, it would be at 1 molar. All right, so again, this right here, the delta H 0F, means the enthalpy of formation at standard state. That is something that you can get from the tables. Those tables are available through Sapling or through the Integrative Chemistry book. Similarly, in this equation, the N and the M here represent the number of moles or coefficients from your balanced chemical equation. And then finally here, this symbol symbolizes sum. So what we're going to do is that to calculate the enthalpy of the reaction at standard conditions, we're going to be adding the product of the coefficient times the enthalpy of formation for each of the products. So we basically have one parenthesis for each product where we multiply its coefficient times its enthalpy of formation. And once we add everything for the products, then we're going to subtract the same summation or the same addition for each of the reactants. So the reactants are subtracted. You guys might remember this equation from General Chemistry 1. We used to say products minus reactants, each of them with their coefficients. Now, one thing to remember here is that the enthalpy of formation for elements in their thermodynamically stable form is equal to 0. For example, if you have hydrogen gas in the H2 form or oxygen gas in the O2 form that we discussed in the previous slide, then those would have an enthalpy of formation that is equal to 0. And so you would actually not find them in the table, because any element in its elemental form would be known to be zero, so they won't necessarily be in the table. All right, the second one that we have is actually the same equation, but for the calculation of the standard molar entropy, or delta S0. The zero represents standard conditions again. Notice that the equation is the same. It basically says that the entropy change at standard conditions for the reaction that we're looking at is going to be equal to the sum of the product of the coefficient for each of the products times the entropy at standard conditions for each of the products. All of the products get added, and then that's going to be subtracted by the sum of the products of the coefficient of each reactant times the entropy at standard conditions for each of the reactants. Where do we get those entropies? Well, from the same table actually where you're going to find the enthalpies and the Gibbs free energy. Those tables are going to be table 18.1 and appendix 8.2 of the online book. Or else within the homework itself, you would probably find just a link to the table. Now, remember how in the previous slide we said that the enthalpy of formation is equal to zero for each reactant, or for, I should say, for any element in its thermodynamically stable form. However, the same thing is not true for the entropy. The entropy at standard conditions is not equal to zero for any element in its thermodynamically stable form. Because the fact that entropy is talking about disorder, and we said that the only way to achieve zero disorder was if we had a pure crystalline substance at 0 degrees Kelvin, and 0 degrees Kelvin is not standard conditions, right? So basically you will go to the table even if you have an element in its elemental form, and you will find a value for the entropy or standard molar entropy for those elements, which is not going to be zero. I'll go ahead and mention that in section 18.2, these examples, 18.3 and 18.4, and the practice problems with the same numbers, are going to show you how to do these problems. I will show you some examples as well, but these are more examples for you, and take a look if you're still confused. The last calculation is actually the same exact equation, and is for the calculation of the Gibbs free energy at standard conditions. We actually have two ways to calculate it. One of the ways is using the equation that we already knew, that delta G is equal to delta H minus T delta S, but notice that now I have included the little dots or little circles indicating that the Gibbs free energy change at standard conditions would be equal to the delta H at standard conditions from the tables minus the T delta S 0 at standard conditions again. Or alternatively, we can use the same type of equation that we utilize for enthalpy and entropy, which is now going to say that the Gibbs free energy change at standard conditions is going to be equal to the sum of the product of the coefficient of each product times the delta G at standard conditions of each of the products, minus the sum of the product of the coefficient times the Gibbs free energy change for each of the reactants. Where do we get those delta G's? From the same exact table that I mentioned in the previous slide. Now, in this case, what else do I want to say? No, that's it. So just to remind you, oh, and yes, I did forget to say here. Sorry, I apologize. What I forgot to mention here is that for elements in their most thermodynamically stable form, the delta G will actually be equal to 0. And that's actually summarized here. So remember, for an element in its standard conditions, the delta H or enthalpy change is equal to 0. That's the enthalpy change of formation is equal to 0. And the reason for that is that enthalpy of formation represents the energy required to reach that state for that element. But the element is already formed, so it doesn't need to be formed. So you don't need any energy to reach the most thermodynamically stable form of that element because it's already that way. The Gibbs free energy of formation at standard conditions for an element in its thermodynamically stable form is also equal to 0, but the entropy of the element is not going to be equal to 0, because the only way for something to be equal to 0 would be if it was a 0 degrees Kelvin and it was completely pure and in its crystalline form. And 0 and the standard conditions is 298 Kelvin. Therefore, we're not talking about the conditions at which entropy would be equal to zero. So just remember that again, the entropy would be not equal to zero, but the other two will be equal to zero for an element in its elemental form. All right, let's go ahead and do some examples. So in the first example, we're actually going to calculate all three: enthalpy change, entropy change, and Gibbs free energy at standard conditions. And we're going to do it for this reaction where we have SO2 reacting with oxygen to form SO3. So this reaction is carried out at 25 degrees Celsius and 1 atmosphere. As we're reading it, we might already see that this and this is telling us that we are at standard conditions. And then the question is, calculate the enthalpy change, entropy change, and Gibbs free energy with the little circles indicating standard conditions again, using the following data. And the data that we were given is a list of the substances with the enthalpy of formations for each and the entropy for each. Now, my first question to you is, why don't we have anything listed for the oxygen here? Why does the table not have oxygen in the delta H of formation, the enthalpy of formation? Well, the reason for that is that the enthalpy of formation of an element in its elemental form is equal to zero. Oxygen as O2, that's the thermodynamically stable form, or that's the elemental form for that particular element. So the number here is zero. And again, this might not be actually available in the table, so it's something that you need to know. All right, before I actually move to do the problem, I also wanted to mention that there are other examples and practice problems that are going to be doing very similar calculations in your book that I encourage you to look at, especially if you want more practice or if you are confused. So how are we going to use this data to actually find the information that we're being asked? Well, notice that we have the enthalpy of formation for our reactants and our products, and so we can utilize it to calculate the delta H zero by doing the products minus reactant equation, the long equation that we had in the previous slides. We can do the same thing for the entropies, but we don't have a table for the delta G's. So what we're going to have to do is that once we are done calculating the delta H and the delta S, we can then calculate the delta G by saying that the delta G is going to be equal to our delta A, come on, start working, delta H minus our temperature times delta S at standard conditions, right? So once we found this and this, we can come and plug them into this equation to get our delta G zero. All right, so let's get started. We're going to first calculate our delta H for the reaction by taking the sum of the coefficient of each, let me see if I can write that better, the sum of the coefficient of each of our products times the delta H of formation at standard condition for each of the products. And to that, we're going to be subtracting the sum of the coefficient, which I'm going to call M for my reactants, times the delta H of formation at standard conditions for each of the reactants. Great. So what does that mean? Let me position myself here. What that means is that I'm going to take the delta H reaction and I'm going to say, okay, my first product is going to be, actually I should have looked at the equation. My only product is sulfur trioxide. So I'm going to come to the table and I'm going to find sulfur trioxide. So I'm going to say, okay, negative, I'm going to put it here, if you don't mind. I'm going to leave a parenthesis for my N. I'm going to put my negative 395 here for my enthalpy change, 395.7 kilojoules per mole. Great. Now the coefficient, that's the coefficient for that SO3, which is equal to 2. And notice that we just did this. Now we don't have any other products, so we don't need to add anything else. That's it for that term. Now, and I'm going to go ahead and close it in brackets just to keep things neat. Now to that, I'm going to be subtracting all of my reactants. So for the reactants, I do have 2 reactants. I'm going to start with the coefficient for the SO2, which is A2. Notice coefficient for SO2, that's A2. And I'm going to multiply it by the enthalpy of formation at standard conditions for SO2, which is right here. That's a negative 296.8. Oops. 6.8. And that is also kilojoules per mole. And to that, I'm going to be adding, because I'm doing a summation. Everything is being subtracted, but I'm summing now all of my reactants. The next one is for oxygen. For oxygen, the coefficient is a 1, and since it is an element in its normal thermodynamically stable form, we said that the enthalpy of formation was equal to 0. So that term actually doesn't really matter. It goes all the way to 0. So now that I have everything set up, I can go ahead and actually do the calculation, put this into the calculator, and what I ended up was that my enthalpy of the reaction, and I should go ahead and say that this is at standard condition, is going to be equal to negative 195.8, and the units are kilojoules per mole. All right, so notice that this means that we have an exothermic process. One thing that I get people asking me is, does it matter if it says reaction or not? It does not matter. That's the enthalpy of the reaction, or you could just call it delta H for that process. It doesn't matter. It does matter that you put that little 0, because that little 0 indicates that we're working at standard conditions. So it's a good idea not to drop that. All right, now we're going to do the second part, which is to calculate the entropy change, right? So we're going to use kind of the same equation, basically saying that now our entropy change at standard conditions is going to be equal to the sum of the coefficient times the entropy. Let's call it like this for each of the products, minus the sum of the coefficient times the S or entropy at standard conditions for each of the reactants. Again, products minus reactants, each of them with their coefficients. So to begin, again, we're going to start by looking at the SO3. And let me minimize this a little bit so that hopefully we can see everything, kind of. All right, so notice that we have SO3 as our product and the coefficient is A2. And I'm going to go ahead and use my brackets, and I'm going to multiply it by the entropy at standard conditions for that SO3, which is 256.8. And the units in this case are joules per Kelvin, mole or mole Kelvin. I'm going to put mole Kelvin because that's what I usually use. That's the same thing. It doesn't matter if you do mole Kelvin or Kelvin mole. They're both multiplied by one another. The order doesn't matter. Since I don't have any more products, I went ahead and closed the bracket. And to that, I'm going to be subtracting everything for my reactants. In this case, I do have 2 reactants and none of the numbers are 0, so I do need to write everything. So for my first reactant, which is SO2, the coefficient is a 2. And then the entropy for that one is 248.2. And the units are joules per mole Kelvin. And then to that, I'm going to add the other reactant, which is our oxygen. And the oxygen, I have run out of space, I apologize. The oxygen has a coefficient of 1. And it has a value of the entropy of 205.2. And that's also joules per mole Kelvin. Okay, close parenthesis and close bracket. Now, one thing that I usually get people making mistakes on is the fact that you have now 2 operations here that are within the same bracket. So it's really important that you either do them in pieces, like do this calculation in one piece and then this calculation in another piece and then subtract them from one another, or that you're very careful with utilizing your parentheses to make sure that you don't end up doing the wrong sign, because remember that this negative sign is affecting this positive sign here. So either you type it exactly as it is right here, utilizing like a double parenthesis, or you are very careful and do them separately, or you go ahead and multiply this negative in here and get rid of the brackets and say, okay, minus this minus this. So once I plug this in, I ended up with my delta S being equal to negative 188.0, and that's in joules per mole Kelvin. Now, before we go to the next step, remember that the last step was going to be to find the delta G by taking the delta H that we already found minus the T times the delta S. Remember that in this equation, we need to make sure that we have the same unit type for our enthalpy and our entropy. Notice that our enthalpy right now is in kilojoules, while the entropy is in joules. So I'm going to go ahead and change this to kilojoules, and I do that by dividing by 1,000. So this is the same thing as negative 188. And that's kilojoules per mole Kelvin. Now, what we're going to do is that we're going to do the last step, which is to calculate our delta G by taking the delta H that we already calculated, and the delta H, and of course remember that we're still working at standard conditions, so we want those little zeros if the tablet lets me write it. Delta 0 minus T delta S at standard conditions. The delta H was negative 195.8 kilojoules per mole, and that is minus the temperature. The temperature at standard conditions and in this problem was 298 Kelvin, and then that's multiplied by our entropy change, which is negative 0.188, and that's in kilojoules per mole Kelvin. And once you are done writing and subtracting, then you should get the answer as negative 139. So give me a second. Kilojoules per mole Kelvin. Notice that the kelvins actually cancel away, and so both terms are in kilojoules per mole. And as I mentioned, the answer is negative 139.8 kilojoules per mole. The end. All right, so before we move on from this problem, I just wanted to point out that we have a delta G that is negative. What does that tell us about this particular reaction? It tells us that at this temperature, it is a spontaneous reaction. Right? The delta H similarly told us that this was an exothermic reaction that releases heat. And since we have a negative delta S and a negative delta S, that means that this system would only be, let me say that again, the delta H is negative and the delta S is also negative. That means that this system is only spontaneous at temperatures that are lower than a particular threshold. We actually did not look for what that temperature is, but it will only be, it would only occur at low temperatures. It would only be spontaneous at low temperatures. All right, let's move on to the next example. The next example is to calculate the Gibbs free energy at standard conditions using the data from the appendix for the combustion of methane, and that's all that I'm telling you. So to be able to utilize the table that contains the delta G's and the delta H's and the delta S's, you need to have an equation so that you can use the products minus the reactants, right? So the first thing that we're going to do is that we're going to write the equation, which methane, by the way, is CH4. And a combustion reaction is one where we take this hydrocarbon, we react it with oxygen, and what we form is CO2 and water. And this is a reaction that you guys learned in General Chemistry 1 many, many times, I'm sure. All right, from there we have to balance that equation to be able to have the right coefficients. And so we begin with the carbons. We have one carbon here, so they are fine. The next thing that we're going to look at is our hydrogens. We have 4 hydrogens here. We have only 2 hydrogens here, so I'm going to go ahead and add a coefficient of 2 on this side. Now that changes our oxygens, so we can see that we have a total of 2 oxygens and 2 oxygens. That's a total of 4 oxygens on the right hand side. And on the left, we only have 2, which means that I'm going to have to put a coefficient of 2 to make it 4. That basically does it. The other thing that we're going to need before we can go to the table and get numbers is that we actually need to know if these are solid, liquids, or gases, because the table might have the same compound or the same molecule, the same element in all 3 forms, and we actually need to know which one we need because the numbers are going to be different otherwise. So methane is a gas, and our oxygen in the atmosphere is also a gas. The carbon dioxide that we release is a gas, and finally the the water that is being released in this particular combustion is going to be in the gas phase as well. So having said that, we basically go to a table in the appendix and we get the values. And I'm going to just go ahead and write what I found. So the delta G of formation at standard conditions in the units of kilojoules per mole is the following for these elements and compounds. Actually, I should just write it underneath each of these things. So here my delta G0 for formation in kilojoules. Let me write please, kilojoules per mole. For the methane, it's negative 50.8. For the oxygen, what do you guys think that I found? Well, we said that the Gibbs free energy is equal to 0 for an element in its elemental form. For CO2, we found that it was negative 394.4. And finally, for the gaseous water, it was negative 228.57. All right, so now that we have that information, we can go ahead and do the calculation. And basically it's the same equation that we used in the previous problem, where that delta G0 is going to be equal to the products minus the reactants. In this case, I have 2 products, so I'm going to start with the CO2. I have a coefficient of 1 times my Gibbs free energy change, which is negative 394.4, and that's kilojoules per mole, plus my other product, which in this case has a coefficient of 2 for that water, times the negative 228.57 kilojoules per mole, close bracket for my reactants, and to that I'm going to be subtracting the same kind of bracket for my reactants now. So for my reactants, I begin with the methane. Methane has a coefficient of 1 times the value of the Gibbs free energy change at standard conditions for methane, which was negative 50.8 kilojoules per mole. And then I'm going to add my other reactant, which has a coefficient of 2. And for that oxygen, the Gibbs free energy change was equal to 0. So this didn't really matter because that term goes to 0. Once you plug this into the calculator, you should get negative 800.7 kilojoules per mole. And one thing that I forgot is that actually the values that I have put here are just slightly different than the values that you have in your sapling book. And so the number is going to come just slightly different than if you do this by yourself. So I encourage you to do it. The value that you get with the other numbers is going to be about negative 801. So it's not that far off. All right, the last thing that I want to mention in this video is how to compare the treatment of the thermodynamic variables, meaning enthalpies, entropies, and Gibbs free energy, if you were to alter your equation. Once you have an equation, for example, the combustion that we just did, for which we found the Gibbs free energy, what would happen if you multiply the coefficients of that equation by a constant? What would happen if you reversed that reaction? What would happen if you would take two reactions? How do we combine those Gibbs free energies or enthalpies or entropies? So what you need to know is what's in this column. This is the important column for this particular chapter. If you are to multiply an equation by a coefficient, let's say that I multiply all of my coefficients by 2, then the Gibbs free energy, the entropy, and the enthalpy changes are also multiplied by that same number, multiplied by 2, right? If I reverse the equation, then the enthalpy, entropy, and Gibbs free energy are going to actually change in sign. For example, if they were negative, they would become positive instead. And finally, if you have two equations and you add them together, then the values of the enthalpies, entropies, or Gibbs free energy of the two equations would actually be added. These are the same rules that you utilize in General Chemistry 1 when you were treating the enthalpies. But I'm putting here the other things that we have done in this semester where the rules were very different. Remember that whenever we were working with equilibrium constants or K's, if we multiplied coefficients, then we would raise the K to that value. If we reverse the equation, we would take the reciprocal or the inverse of K. We would do basically 1 over the old K to find our new K. And if we added two equations, we would actually multiply their equilibrium constants. So I'm putting this here because we're getting close to the final exam, right? And in the final exam, you're going to have to be doing both of these calculations. And so it's really important for you guys to see the differences right now in what you do if you're working with a thermodynamic variable versus if you're working with an equilibrium constant, okay? So for this particular chapter and for this coming exam, these are the rules that we're going to be utilizing because we're working with thermodynamic variables. But whenever you get to the final, you have to again remember that the rules are very different for your equilibrium constants. All right.